is to show the contrapositive of the reverse direction. So, the negation of causally compound is that you're causally primitive. We need to show also that if you're causally primitive, then that implies that the language is temporally simple. So all actions are causally primitive. I'm not going to go into as much detail here, but the crucial property is that a causally primitive action forces you to state every non-trivial statement over one interval. Okay? And that interval I call the critical region. And the nice property about critical regions is, let's say we have this hypothetical red mutex here, then in that case the critical region of light blue has to be before the critical region of purple. So what's the proof? We take all the parts of compound actions that happen to be causally primitive and move them to the front of the suffix and then continue on. So by the end of this induction, we'll have placed all action parts contiguously, which is the definition of classically sorted, which is the definition of this plan does not require concurrency. Okay? So we can prove we can do this for arbitrary plans if always every operator is causally primitive. That establishes the reverse direction. So, a language that permits causally compound actions, which is a very cheap to test syntactic condition. You can just look at an action and say, are you causally compound? Expresses required concurrency, and that's an if and only if. Testing required concurrency is, of course, not efficient at all because that's a quantifier over all possible plans. So, it's a very nice theorem to have. There are two more theorems that I'm not going to prove for you. These are the compilability theorems on both sides of the expressiveness divide. We'll briefly state them. A proper compilability theorem is like this one. Every temporally expressive language compiles into interleaved temporal planning, which means that interleaved temporal planning is representative of the entire upper side of the figure. Technically, the simple side needs some scare quotes, but it's close enough for the conclusions I want to make. So the theorem is that first fit is a dominance reduction on every temporally simple language. An earlier theorem was that first fit is a dominance reduction on conservative temporal planning. So what the theorem is saying is that first fit is dominance reduction not just on conservative temporal planning, but also every temporally simple language. All right. In theory, unless I was going way too fast, I have actually already spoken for an hour. But we could talk more if anyone's excited.
So you should continue this part.
Continue this part? All right. So, for the algorithm analysis, there are three kinds of forward chaining planners that we want to analyze their properties in terms of being able to do temporal planning. The skeleton of a forward chain of a first fit classical planner is to take a classical planner and integrate it with first fit. So what does that look like? Here's the search routine. Pick a candidate out of the queue, check whether it satisfies the goal. Non-deterministically choose to add an action to the plan. And whenever we want to, we can greedily schedule the sequence of actions in order to check its temporal properties. Okay? So basically, you take any classical planner you want, LPG, MIPS, and you add this wherever you like. It can be strictly post-processing, it can be per search node. Doesn't really matter. Now, of course, to actually make this work in practice, there are, of course, a number of planning techniques that you need to implement in order to make the combinatorial search at all possible. Which is worth keeping in mind. Okay, so the results are that this general strategy can be assumed to be systematic. If you start with a systematic classical planner, then it's still going to be systematic. And then there's an interesting distinction here between conservative temporal planning, where we take out deadlines, or if we leave deadlines in. I didn't talk about it, but the definition permits deadline goals. The reason this is interesting is because if you can say deadline goals, that is, and you're complete for that, that's the same thing as being optimal for the language. Okay? This is just the standard reduction from an optimization problem to a decision problem. So that's why it's interesting to split this up into two cases here. And then what I'm saying is that without deadlines, this is guaranteed to be complete by the theorems of chapter 3, essentially. Here, this depends upon whether or not you're willing to take the techniques of multi-objective search and add those into this picture in order to do multi-objective search efficiently. And then also the results for interleaved temporal planning are simple. Just because it required concurrency, this can't say required concurrency because it uses first fit to schedule action sequences. Okay, so those results aren't difficult to prove. Now, if we want to do interleaved temporal planning, then it's clear that, at a technical level, that we can't use classical planners to just integrate them with first sphere. We need a better idea. So an idea that was created here by Feenbachis and Michaelati is termed, as I recall, term created by Dan Welt here, decision epoch planners. The notion is that you maintain a current time, or an epoch, or a now, and you search through the space of all schedules of actions by non-deterministically choosing whether to dispatch an action at the epoch, or whether to advance the epoch to a later event that you already know exists because it's an end part of one of your earlier actions. So just asked a question earlier about why the definitions define things in terms of sequences. So decision epoch planner, we notice here, if it takes multiple choices to dispatch an action now, it has k factorial ways of doing that all mean the same set. So if you want to do this efficiently, you should implement the de-ordered equivalence reduction. Okay? Now it's important that it be able to do that because branching over sets directly would be even worse. Okay. So then we have our results about when this is complete and when this is systematic, which is in general it lacks all the theoretical properties we would like. As I mentioned earlier, we shouldn't walk away from this thinking, oh, decision epoch is a bad idea. It's just that we should use this theory to better inform what problems we apply it to and how. Yes?
So a point about the set. See, when you do, say, release databases, right?
Mm-hmm.
So the theory is about sets. Now, when the algorithm runs about finding something from databases, they, of course, do it in sequence. So I would expect the theory to be about sets. And I think, a lot of the theorems about whether a particular algorithm or particular approach of getting those sets might not be correct or not could be simpler if you do with respect to the sets.
That is the normal order that you do things in. Normally you set up the natural definitions of what the problem you want to solve,
right.
And then your theorems are about how to implement it efficiently.
Right.
I'm trying to reverse engineer specifications that don't exist. I'm looking at the state of the art. These are algorithms, they exist. I can study their properties on test problems.
Right.
What I'm trying to prove is not how to implement it efficiently. I know it can be implemented efficiently, I just don't know what
No,
it
if they
is.
if they find the sets, you're trying to see if those algorithms find the correct sets and under what circumstances they find.
Yeah, that's part of it. Also, so something that's not obvious and I didn't talk about in depth is that every state-of-the-art system is supposed to nominally be a P2DL temporal planner, but nobody implements that specification correctly. Okay.
Right, and that's what you're proving in many of your theorems.
In order to do these proofs,
Yeah.
I need to have a formal semantics to do proofs in.
Right.
There is no formal semantics that is actually correct for describing the state of the art because the state of the art doesn't correctly implement the only specification that's written down. So one of the contributions of the dissertation here is to write down a correct specification, and that's why the theorems and definitions are a little backwards.
This means okay. We can continue. We will discuss it. We'll discuss in shades.
All right. So a different idea for doing complex forms of temporal planning is to use a very general concept of constraint reasoning or temporally lifting. Instead of picking the dispatch times in the schedule as part of your search process, instead of searching through schedules directly, as decision epoch planning does, instead, what temporally lifted planners do is they search through sequences of effects. So we non-deterministically choose to add effects to the end of the plan, and this means we're searching through effect sequences, not through effect schedules. Whenever we want an effect schedule, we use the rescheduling theorem to tell us that we only have to consider optimal solutions to the simple temporal networks induced by the effect sequence. So basically, whenever you want, you can convert the exact effect sequence into an effect schedule, and that is a complete approach to interleaved temporal planning. And if you implement it just so, then it will also be systematic. So I'd like to talk a little bit about what that really looks like, because otherwise you're going to have a very active imagination to see what temporally lifted planners do. So this is a match fuse domain. It's a common example. There's a lot of noise going on here that standard planning techniques eliminate by virtue of using reachability analysis. So standard planning techniques would be able to see that these are all dead ends and would be able to prune them, so we don't have to pay attention to them. What a temporally lifted planner does is it takes the parts of actions here, like light, end match, start fixed fuse, and end fixed fuse, and builds this tree on all ways of sequencing them. Okay? And then we can calculate We don't know what time we're going to start this, but because of the precise way the definitions are written down, we don't need to know what time it is in order to know that starting fixed fuse does nothing, and that starting light match means that we can see. And ending fixed fuse means the fuse will be fixed, and if we end the match afterwards, then we'll have achieved the goal of fixing the fuse safely, assuming that this can be scheduled. Okay, so that's the integration of the constraint reasoning divides this up into sort of reasoning about causality and reasoning about the temporal constraints. There's an interesting difference here between the details concerning this node. In 2007, I would have pruned this node by saying fixed fuse's duration is too long. So down here, it won't be possible to finish like the light match action. The light match action has a shorter duration. So you would build a simple temporal network here and realize that it is cyclic, and so you can't solve it. In 2012, instead of saying that the semantics here are that it's a totally ordered sequence of effects in time, instead things only depend on what they causally interact with. So the ordering constraints here are that you have to occur after everything that writes to your dependencies. So the precise definition of what a corresponding simple temporal network is slightly different, and that means that if you wanted to prune this node, it's a different theorem. So in 2007, it was based on inability to schedule once you get down here. In 2012, something interesting happens. We're actually at the parents of these. We can notice there's an earlier problem. Beginning the lighting of a match and beginning the fixing of a fuse are causally independent of one another. Okay, these things don't interact. So the subtree here is going to be exactly the same as the subtree here. It'd be a waste to explore them twice. The deordering theorem tells us it would be a waste to explore them twice. It doesn't tell us how to detect this efficiently and avoid this wasted computation. So I have here sort of a more in-depth look at how you start from the naive approach to temporally lifted planning and progressively implement the theorems in order to get to a more and more efficient form of temporally lifted planning. I don't think I want to go through it in a super amount of detail. So I think just to sort of sketch the idea, we start from a really large tree and then we reduce it by one set of techniques, and then here we're able to see that light match and fixed fuse is the same as fixed fuse and light match, so we're able to prune this node by a nice, efficient computation. I would like more eyes on this proof because it seems too easy to work, but I've hacked on it, like counted on 3 times, or whatever. It seems right to me, but this is extremely promising computational, very simple. Okay, so, summary. There are 3 kinds of temporal planning we should sharply distinguish between because the differences matter computationally, both empirically and theoretically. One of the major contributions of the dissertation is to actually write down what the definition of temporal planning is that the state-of-the-art temporal planning systems do. I prove, more or less, that that is actually the case, that is what these systems do. As well, some of the corollaries here have some very nice computational implications for how you can try to improve the state of the art. This is more of the proof that this does describe the state of the art. And then this is just a nice comprehensive look at properties of algorithms, which is always a useful thing to have. Thank you.
So the public presentation is over. The floor is open for any questions from all the audience. Yes.
I have a question regarding the model of time. So maybe a solved problem from the different communities, so maybe you can explain it to me. Fox and Long describe the directed action in 3 phases: begin and overall and constraints that are specified for each of the phases. Do you feel this model sufficient to solve all the problems, or maybe just want to prove?
The definitions I'm writing down are meant to replace the definitions of Fox and Long, because the definitions of Fox and Long are incredibly difficult to implement. They can be implemented, but you have to use the theory of hybrid automata, which sort of violates my goal of what is the temporally simplest extensions of strips that are meaningful, so I want to stop before getting to hybrid automata. So the long-term goals of Fox and Long have actually finally been met. They've implemented a system called Colin, which is concurrent linear change, is what they're able to plan with. And that was their aim way back in 2002. They wanted to plan with continuous change. So they set up a definitions of temporal planning whose discrete case is meant to be generalized to continuous change. And because of that, their discrete case is significantly more complicated than actually makes sense for discrete temporal planning. So all of the engineers who are trying to win the competition says, those are silly semantics, and we would waste a whole lot of time. We know how to solve these problems. We see the benchmark problems. We see a different semantics that will allow us to plan much more efficiently. And in fact, there were two different versions of that. So the subset of the community that won the temporal planning competitions looked at PDDL problems and ascribed the semantics of conservative temporal planning. So they didn't look at compound actions as consisting of an at start, an overall, and an at end. They computed those functions and then did the sequential composition of those functions, and that became the entire semantics of their actions. So that was a pre-processing that's done by LPG and MIPS, and is important for their empirical performance. So does that somewhat address your question?
But I also see from the slides that your action still contains those prefaces.
Yes, no, I mean it's meant to be sort of a plug-in replacement to PDDL syntax. One of the differences is that instead of instantaneous effects, all effects have positive duration. Okay, and that's because that's what the systems actually implement. If you want to have zero duration actions, you have this zero duration effects. Then you have this divided moment problem, where I remember so clearly because I was so happy. Tuan started as a graduate student, and he was looking at the Rover's domain model in PDDL, and he says, "How does this work? At start, you have to be at location alpha, and then at start, an effect is that you are not at location alpha. So are you or are you not at location alpha when you begin this action?"
I think they introduced those epsilon times for that.
Right, and they ascribe a particular semantics for epsilon, which is a topic I love talking about at length, but it's a highly technical, and most people feel that it's implementation detail not motivated. But in terms of it, so why Drew McDermott picks the hyperreals is that he has a correct implementation of epsilon. Okay, the right definition of epsilon is in terms of calculus. It's in terms of these epsilon delta limit proofs for continuity, and he uses non-standard analysis of Robinson, which is formulated in the hyperreals, and that allows him to say that those are not zero duration, but epsilon duration for epsilon meaning an infinitesimal. In PDDL practice, epsilon does not mean an infinitesimal. Okay, it means just a really, really small positive number. So effectively, they have more or less said what I've said, which is that all effects actually have durations. So time is actually not even close to the hyperreals or the reals. It's actually just integers at the end of the day.
Yeah, I have. If I understand your theorem correctly, you're saying that with what you can express for this required concurrency, you couldn't express originally with with classical sequential planning?
Well, sequential planning is piece-based complete, so you can say anything you want.
Okay, so that's okay.
Okay, but in order, it's actually helpful to consider that. Okay, so how do you say that?
I mean, you add so many constraints and widgets that have to look appropriately.
Right.
I mean, I understand that.
But I can say a little bit more about those widgets. Okay, what exactly are they? They consist of writing down interleaved temporal planning, solving it, and then writing out the algorithm into the classical planning model.
No. You can.
That's what piece-based complete means.
If I want to say two things are concurrent and have to happen at the same time, you can say I don't care which one starts, but then making sure when that starts, it will set something that it forces the other one that's concurrent to any sequential planner to happen immediately, just touching it. So that's like concurrent.
Sequential planning doesn't actually let you syntactically say that.
But
in order to say that, you can model it by modeling a different form of temporal planning and an algorithm which is complete and systematic for that form of temporal planning. And then your classical planning model is a model of the machine which solves the problem that you want to solve. That's what completeness theorem is about. It's you can express any Turing machine that solves the problem in the complexity class by modeling the actual computation traces of the Turing machine. That is the proof of the original.
I'm talking about specification, not the computation.
Right. The syntax of classical planning does not let you talk about concurrency at all. So you can't say that something is
But
temporarily.
you can let me say, I mean, an action is enabled or not enabled at a given time, right?
No.
No?
There's no time.
Enabled or not enabled?
Yeah.
In a given state.
Right, in a given state, yes.
Okay, so I mean, if I execute one action and I want the other action to execute with it, it will enable just that thing that will make the other action execute and no other action execute. So you change the requirement for every other action. So once that action that executes and has a concurrent action that needs to execute with it, then every other action becomes disabled and only that action that's concurrent with it can be enabled.
So if you go that far, then what you've built is this tree without the quantitative temporal constraints. So you can do that. You can take all the parts of compound actions and represent them as strips actions and drop all of the duration constraints. And if you drop all the duration constraints, then there is no question here about, say, whether this is a solution. Okay, it just is a solution. This is not. We have to solve a separate constraint program in order to know whether or not this is a solution, because the model actually talks about values of time. The model you're talking about in classical planning, there's no way to attach an upper bound on how long the. I should use a real example. So.
I mean, these are not interesting, but just want to understand what does the theorem say. I mean,
So you can take these and you can make these strips actions, all right? And then when you do a state transition, for example, begin light match will be possible. And begin light match can set visibility to true, all right? And in fact, that's exactly what it does. And that could just be an independent action that has no connection with finishing light match, okay? And so then you would have visibility, and you could do this at any time in the plan. You could schedule 1,000 other actions first, and then do this, and then include finishing the burning of the match much later. So what interleave temporal planning allows you to say is that when you schedule these cannot occur arbitrarily far apart in time. All right. It actually allows you to attach durations to the effects, as well as durations to how long the total process can take. What you're saying is very important. I mean, that is the way that you go about efficiently implementing temporally lifted planning. That is the idea. Leverage classical planning as much as possible. I guess what I'm saying is that to get every little detail right, you need to, and in the right way, you need to step into the code and modify it.
I'm not talking about the implant, just the theorem. What does it say?
So
because you're saying something is not possible to do, I mean, if I understood you right, in classical planning system.
Yeah, well, no, I mean, so it can't say required concurrency because it has no model of time.
And they couldn't simulate, you cannot simulate it in the specs of the
No,
problem.
of course you could simulate it
in the
because
specs
it's
of the
basically
problem. In the specs of the problem, not the implementation. In the specifications of the problem.
the only way to talk about time in strips is to add to the model a definition of a different temporal planning formalism. Strips does not actually allow you to say anything about time or durations or deadlines. You can force strips to reason about deadlines by giving it an algorithm to reason about deadlines in its model. Or you can step into its code and modify its code, which is the same thing, really. So you can think of a classical planner as a virtual machine. And the question is, do you want to change the virtual machine, or do you want to change the program that you're inputting? Programming in
to make it
PDDL.
very simple, sorry, I took too much time on this. You have a specification for it in temporal language, right?
Yeah.
Can I take it automatically translated to a specification that strips with
Yes.
That's the question.
Yes,
Can you do that?
Yes, that is the reduction theorem here.
Okay.
So you will get a strips problem where the number of states is multiplied by 2 to the 32 because you'll write out 1 Boolean fluent for every bit of a value of time.
So ultimately it's an efficiency issue.
So you don't have a polynomial transformation, you can say.
No, you can do a polynomial transformation. It's just that a polynomial blowup given to an exponential time algorithm is an exponentially significant thing.
So is it a polynomial
So you
thing
can
or-
do that. Okay.
Yeah, this is a polynomial
Okay, so
reduction
that I
into a
missed.
finite transition
That I
system.
missed.
So this is the complexity class statement. This is the methodological. What really can strips say in a computational
Okay.
theory sense. But this is so. This is impossible because there are infinitely many values of time. It doesn't help to reduce this
Right.
to exponentially many values of time.
Karthik has a question from
So
Mausa.
we have an email question from Mausa. So he's not on.
Okay.
Awesome.
So, no, he's following along, but he can't talk. So okay. So Mausam's question is basically, so he thanks you for the in-depth characterization of temporal planning. His question is, he feels that the results that you've stated here apply mostly only to the subset of temporal planning that's allowed by PDDL 2.1. And he is proposing some extensions to PDDL 2.1. These are just things that he's proposing, and he wants you to say, if you can say anything about, what might happen to some of these things in light of those extensions. So there's 4 of them. The first one is simple processes. Yeah, I mean, this is a big question. So the first extension is simple processes where a temporal action is a process. Preconditions.
I think this is detailed enough that it has to be done in the closed session or offline.
It's possible. I can forward the email.
I mean,
Yeah,
the short answer is that I would love to talk about
Okay.
standardizing
Okay.
and actually getting this research out there and getting people to agree to
I think
specifications.
Dan is very good
That's
at running time.
a lot of additional work though, because you have to get
Okay.
He has to
multiple
be
people to
12:30.
agree.
Okay. I'll
11:30.
No, 11:30 each time is 12:30 hours.
I'll forward this question to Rao so you guys can
Yes,
talk about it.
yes.
So can we at least hear the list?
Yeah. So,
Yeah.
so,
Yeah.
so the 4 extensions he proposes. The first one is simple processes where preconditions may be required at intermediate points and overall may be over a duration. So that's simple processes. Second one is processes with continuous change, so fuel being filled in proportion with time. The third one is interruptible actions, actions that can be interrupted at any time or some set of allowed interruption times. And the fourth one is just duration uncertain.
Yeah, I mean these are all very interesting
Right, so I'll forward this
extensions.
down.
The first one is sort of possible without greatly complicating the computational complexity. The other 3 are a lot of fun.
So email Mausam that there is a good reason why we muted him. By the way, for those of you who don't know, I mean, Mausam was one of, he mentioned Mausam multiple times in the talk, and he's one of the co-authors of the original paper, and the original paper would have had many more citations if Mausam had a last name.
Yes, I know.
He actually lost a whole bunch of citations because he doesn't have a last name, but that's a different story.
So the automated scanners can't understand that someone could have only one name, so they break.
Other questions?
Can you explain to me how you